Hi guys, welcome to your next video lecture. This is for Chapter 2, Section 1, which is our next lecture on our topics that we're going to be covering in this class. So I'm going to go ahead and begin by sharing my screen so we can go ahead and get started. So, okay, so it's going to pop up there in a minute. There it is. All right, so let's start by thinking a little bit about how we explain concepts to children, because we're going to get ready to start talking about set theory and the basics of set theory and understanding the elements of how to work with set theory. And the reason why we're doing that is because by understanding set theory helps us to sort of, in very broad and general strokes, understand how it is that we explain some very basic concepts of things like addition and subtraction and multiplication and division, and all those kinds, and some upper level algebraic concepts. It helps us to understand how those things and the rules that apply to them came to be from a more broad and general point of view. It also later on leads to a better understanding of the different types of number groupings that we have. You know, we talk about real numbers and natural numbers and imaginary numbers, and each of those groupings of numbers has a set of numbers or digits that apply to them. And it all comes down from having this basic idea of set theory. So let's pretend to put on your kindergarten hat now. Pretend you're sitting in kindergarten class. You see this display in front of you, and you're asked to count it. Okay? And so you're going to have your first student who is going to count it, and I'm going to go ahead and put something up here for you. Okay? Let's say we have one. If I can get that working. There we go. 1, 2, 3. Okay? And your first child begins to count, and your first child goes like this: 1, 2, 3. And that is not exactly the proper way to count, but that's okay. You just say, okay, thank you. And then you ask the next child to try counting. And your next child counts and goes 1, 2, and then stops. Okay? You're like, okay, that was a good try. And then you give the next child an opportunity to count. And that third child goes 1, 2, 3. Okay? Now, what was the basic difference between the way each of those children counted this group of blocks? It was their understanding of what is a set theory concept called one-to-one correspondence. Basically, the third child that was able to count the 3 colored blocks successfully has an innate understanding that the 3 colored blocks formed a set of blocks, and that the numbers that they know, 1, 2, and 3, also form a set. And they were able to successfully make that one-to-one correspondence between a number and a block, a number and a block, a number and a block. Now, there's also added to that the idea that they're able to understand that those 3 blocks together form a quantity, which is also another concept that we're going to discuss later in set theory. But this is the basic idea. The children who were not able to successfully count all 3 blocks was because, as you saw, they did not necessarily have a one-to-one correspondence between the numbers they knew as a set and the 3 blocks you presented in front of them as a set. So that gives you a quick little intro into our conversation on set theory. Okay, and so here we go. Let's begin with the notes. Get that on the screen more clearly for you. And let's start with a basic definition. Okay, our first topic is going to be sets, and sets are defined, and here's our basic definition. They are defined as a collection of objects, meaning that we can make a set out of anything, just like we made a set of those 3 colored blocks. We can make a set out of numbers. We can make a set out of all your unpaired socks at home when you do laundry. A set is basically a collection of objects that have been defined as having parameters that bring them all together. Okay? The other term that you should be familiar with, and this is this vocabulary term here, and that is here, this vocabulary term that says that you have something called an element or a member. And an element or a member is defined as the objects that are in that set. So once you define what it is that makes the set, maybe you said, I'm looking for the set of all the unpaired socks in my drawer. Those parameters now have defined the set you are creating. Now, every sock that belongs in that set, because it is unpaired in your drawer, is an element or a member of the set that you have defined as the set of all the unpaired socks in my drawer. I know it's kind of a very basic, mundane example, but hopefully that helps you to clearly understand what a set is and what we mean when we talk about elements or members of a set. Okay? Now, there are three common ways to state what a set is. We can state a set by giving it a verbal description, like you just heard me say. So, for example, I could say, I'm looking at the set of all the United States that border the Pacific Ocean, and now I have verbally described the set I'm talking about, right? The other way that we can talk about a set is by listing it, okay? And this is where we use special notation. We use these braces right here, okay? And that brace encloses the list of the things that belong in the set. So for example, here, instead of stating it as the set of all United States that border the Pacific Ocean, my putting the brace here, I'm saying the set of Alaska, Oregon, Washington, California, Hawaii, and you can see that these are all states that have a border with the Pacific Ocean. So I have stated my set using the braces, and it kind of fell off the notes here, but you can see that there is another side for where you put the braces to close your set. Now, everything within those braces is the set you're discussing, okay? Now, the other way that we can define a set is by doing a set builder, okay? And again, these are notations that we use. The notation, and it looks like this, okay? So this is the notation you would use. You would once again still use the brace, which you read as the set. Then in the front, you put in your variable, and this is saying of all X. Then you put this line, which means such that, and then inside, here's where you state it, the variables that you're looking to put inside your set. So you state your set, you go X is a United States state that borders the Pacific Ocean, and then you close it, okay? So you can see here that you read the brace as the set, you read your variable as of all X, you read the bar as such that, you read the blue X as X, and then is equal to, and you would read the words that describe the set. This here, using this notation, is called stating a set using a set builder, okay? Basically, if it makes it simpler for you to think about it, this is the notation for writing out a set instead of just stating it in the full sentence like we did up here. Here is where we didn't use any notation other than the braces to denote that we're discussing a set, and then we actually just listed the members of that set. And here is where we use math notation or set builder notation to mathematically state our set. Okay? Now, some things to know about notation. When we are working with set theory, okay, in notation, we usually denote capital letters, okay? And then those capital letters, if we use, and I'm trying to look for a highlighter here. If we use this symbol here, that symbol means is an element of. If we use this symbol here, that symbol means is not an element of. So here's how you would use us. Here's an example, okay? So if I have S is the set of all United States bordering the Pacific Ocean, then I might state it like this. I might state it as Alaska is an element of set S, meaning Alaska is a state that borders the Pacific Ocean and belongs in set S. Okay? If I write it like this, I'm saying Michigan is not an element of set S. That's what this means right here. Michigan, the symbol is not an element of, and the name of the set, because we usually denote sets, the sets we're talking about, we name them by giving them capital letters. Okay, so if I want to talk about the set of all the unpaired socks in your drawer, I might call that set capital S for socks. So then I would say the set S, which is all the unpaired socks in your drawer, and then I might pick a sock that does not have a pair and say this sock and use this symbol to state is an element of set S. Or if I pick out a sock that has its mate or its pair, I might say these, and I would use this symbol, is not an element of the set S, because set S is defined as the set of all unpaired socks in your drawer. Okay? So those are the first two symbols of notation that we use. So things to remember so far: we name or we label our sets by using capital letters. We use this symbol to mean not is an element, meaning it does belong in this set. And we use this symbol to mean is not an element, meaning it does not belong in this set. Okay? If we use the brackets like this and leave nothing in it, we're saying that this is a set that has no elements that belong in it. Sometimes you will use this symbol instead, which also means there are no elements that belong in this set. Whether you use this symbology or this symbology, what you're talking about is what's called the empty set or the null set, meaning none of the elements that we're discussing belong in this set. Or sometimes we use the same symbology when we're trying to say the thing we're talking about doesn't have a solution belonging to the set of numbers we're discussing. So the answer is null, which is what we refer to as this, or empty set, which is what we refer to as this. Okay? So if it's helpful, sorry about that, this is the empty set and this is null. Okay? So a way that you could use that as an example or in a sentence, you'd say the set B, which is all US states bordering Antarctica, the set B would be set, the empty set, or the null set, because there are no states in the United States that border Antarctica. Okay? The next thing you need to know, when two sets are equal, this is how you write it. Okay? You write the name of each set and set them equal to one another. However, please note, okay, that this is true if and only if they have precisely the same elements. What does that mean? Let's look at the example. If we look at the example, let's say that we're looking at the set of X, right? We're reading the notation, such that X is a state that borders Michigan, okay? This set, the set of X, so that X, such that X is a state that borders Michigan, is equal to this set, Illinois, Indiana, Michigan, and Wisconsin. Why? Because those all border, okay? However, and here's the part you need to notice, which brings us back to what we were saying before in regards to note that you can only state the two sets are equal to each other if they have precisely the same elements. Here's what you're trying to note. If every element in set A, the set of X, which is equal to the states that border Michigan, is not equal to every element in set B, Illinois, Indiana, Michigan, and Wisconsin, then set A would not be equal to set B. So for two sets to be equal, they must contain all the same elements. If one of those sets does not contain one of the other elements, then those two sets are not equal. If one of those sets includes one extra element that is not found in the first set, then those two sets are not equal. Okay? So you have to bear that in mind. I'm going to put a little star here for you so you can remember that that is important, okay? So here are a couple of inherent rules about working with sets, okay? Rule number 1, the same element is never listed more than once. So for example, if we have a set that includes element A and then element A again and then element B, you would never write it like this. You would only write it like this. Doesn't matter if element A shows up twice, 3, 4, or 5 times in the set that you're talking about. When you're writing or stating that set, you would only list element A one time, because listing it one time is sufficient to say that it exists in the set. It doesn't matter if then, when you look at the actual set in real life, element A exists in that set 3 times, 4 times, 5 times, okay? Also, the order of elements does not matter. So you can state it like this, as in the set of A and B, or you can state it as the set of B and A. It doesn't matter. Those two things are the same. They would be equal to each other, okay? Now, just like we talked about in our introduction, let's talk about the concept of one-to-one correspondence, okay? So if you remember from our introductory example, okay, you need one-to-one correspondence in order to oh wow, look at that, can't speak, let's try that again. We need one-to-one correspondence in order to formalize the meaning of a whole number, okay? So here is the official definition of one-to-one correspondence, okay? Here it is. One-to-one correspondence between two sets, set A and set B, is when each element of set A pairs with each element of set B and vice versa. And the notation we would use, and I'm going to go ahead and highlight that for you, is this. You would set A with that little sign, that squiggle, which is called the tilde, okay? You put the tilde in between, and by putting that in between the name of set A and the name of set B, you are saying they are equivalent, or they match, or they have one-to-one correspondence. Let's look at an example. Sometimes a visual is very helpful, okay? So if we define set A as a set such that it includes letters X, Y, and Z, and we define set B as a set that it includes letters A, B, and C, we can note that we do indeed have one-to-one correspondence. They are not equal to each other because they do not contain the same elements. Remember that earlier we defined that for two sets to be equal, they must contain the exact same elements. But they do have one-to-one correspondence because we can pair one element from A to one element from B all the way down. Now, we could do it this way, or we could illustrate it this way, where we match, let's say, X to B and Y to C and then Z to A. But irregardless of how we choose to match them, the fact of the matter is, because each element of the first set, set A, can be paired with an element of the second set, set B, those two sets are equivalent, and we would write them as A is equivalent, okay, or has one-to-one correspondence to B, okay? Now, a little note. Please note that equivalent sets, like A and B, have one-to-one correspondence. So they're going to have this, okay? But they are not necessarily equal. They can be equal if both sets have the exact same elements, but they do not have to be equal, like in the case of our example, and they can still retain their one-to-one correspondence and their equivalence, okay? So for example, we have the set here of numbers 1 and 2, and it is equivalent, right, or matching to set A and B because we can match each element to a pair, right? They are not equal, however, and you can see it here, they are not equal because 1 and 2 are very different elements than A and B. They are equivalent, which is why we can use this symbol, because we can have one-to-one correspondence between both sets, okay? Now, let's talk about what we mean by a subset. This is an important concept, especially as we move on to mathematics, because a lot of times, especially in geometry, we teach things that have subsets. Okay, for example, in geometry, you might talk about quadrilaterals, and the subset of quadrilaterals is rectangles, and the subset of rectangles is squares. Okay, they are all related, but they are subsets of each other. So it's important to understand what we mean by a subset. And here, when we discuss it in set theory, it helps us to sort of generalize that concept. Okay, so a subset, here is the notation we would use. Okay, so I'm going to go ahead and circle it. This symbol right here is the notation we use to say that we're talking about a subset. Okay, and the way you read it is from left to right. Okay, so what you were saying here is that A is a subset of B. You're not saying that B is the subset of A. You're saying that A is the subset of B. So you read it from left to right. A is a subset of B. Okay? Now, to be a subset, this is something that's important to remember. You can be a subset if the sets are not equivalent, but they are related. Okay? So let's look at the official definition of a subset. Here it is. Here's the official definition. Okay? A is a subset of B, and here's the important part, if and only if every element, I'm going to go ahead and underline that, every element of A is also elements of B, even if then B continues on to have other elements in it. Okay, so let's look at an example. Okay, here we have the set A such that A represents all the cities of New Hampshire. Okay, this set is a subset of set B such that B represents all the cities of New England. Okay, so you can see that, think of it as the bigger set is the umbrella, right? And the subset falls under the umbrella. So because the set of B is all the cities in New England, but the set of A is just the cities in New Hampshire, the set of A is a subset of the set of B because all the cities in New Hampshire happen to also reside within New England. Okay? Even though New England, the cities of New England are made up of more than just the cities of New Hampshire. It includes the cities of all the other New England states. Okay? So here's another way to look at it that makes it a little visually easier to see. So we have here is set A, which includes A, B, and C. And we're saying that it is a subset of set B because set B includes A, B, and C, but it also has all these extra guys. Okay? So A is a subset of B because it follows the rule, like we said up here, that it must, if and only if, every element of A is also an element of B. And sure enough, all the elements of A, lowercase a, B, and C, are elements of B. Okay, here's lowercase a, B, and C, even though set B also contains a few extra elements. Okay? So this, successfully, A is a subset of B. So this, we're going to give a check mark. That is a successful example. Let's look at the next example. Here, in this case, we have set A, which includes A, B, and C. And here we're saying is not a subset. That's what it means to put the line through the notation, right? This is not a subset of set B because B has A and B, but it does not have C. Instead, it has D. Okay? And since all the elements of A are not to be found within B, then you cannot say that A is a subset of B. Okay? We can say that they have one-to-one correspondence, right? So we could say that they are equivalent sets, but we cannot say that A is a subset of B. Okay? Hopefully that's clear for everyone. All right, now, here is a concept that your textbook discusses. I feel it's a little redundant and unnecessary, but I'm going to let you see it anyway because it is covered by your text. And that is the idea that this symbol right here means a proper subset. There's really no big difference between what a proper subset is and what a subset is. So I'm not sure it's necessary to make this differentiation. For the purposes of our conversations on set theory moving past this point, we're not going to make that differentiation, but you should be aware of the fact that it does exist, okay? So a proper subset is defined where one set contains more than all of the elements of the first set. So in essence, if we go back up here, okay, this example right here, we could have, instead of using subset symbology, we could have simply used the set symbology, the proper subset. We could have crossed that out instead and just used this, which means proper subset. And we could have said A is a proper subset of B because the definition is where one set contains more than all the elements of the first. And you'll notice that B does contain more than all the elements of the first. But like I said, I'm not sure if that's a differentiation that's important for us to make, but it is the case. As you can see here in the example, I gave you another example of it. Here's set A, it contains A and B. Here is set B, it contains A, B, and C. Therefore, A is a proper subset of B because all the elements of A are contained in set B, even though set B also has these extra elements. Okay? Now, let's talk about Venn diagrams, which I'm sure you've seen. We, in the purposes of this textbook and our conversation, Venn diagrams get used to discuss set theory as well. Okay? So, you know that a Venn diagram is a diagram that represents relationships between different sets. Now, we're used to using them mostly in things like English and history to show a correspondence between different sets of information, but we can also use them here in math, okay? Now, when we use a Venn diagram, it's usually pictured within a rectangle labeled U, where U represents the universal set, okay? So if you see here, here is the square, okay, and you will see that it's labeled U, representing the universal set. And within the universal set, we have set A, set B, right, and set X. Now, based on this diagram, I can tell you that A is a proper subset of B because clearly all of A is contained within B, right? So here's B. And that's not good because you're not seeing what I'm doing here. Let's add a couple more highlighters here. Okay. And we'll add another highlighter. How about, there we go. All right, so let me erase it like this and see if we can do it a little bit better. Okay, so here's our universal set, and we can see that set A, right, is a proper subset of set B because set A is fully contained within set B, right? Set B being the outer circle. So that's why we can make this statement that we have right here, okay, that A is a proper subset of B. Because, and then we can say, and since X, and they're telling you that X, so we're going to point to it here, X is an element, remember that's what that means, of B, okay, but X is not an element, that's what this means, of A, because it's not inside A, right? So everything that's in green is A, everything that's in pink is B. Because X is in the pink part, it is an element of B, belonging to the B set. But because there is no X within the A part, it is not an element of A. So that's why we know that A is a proper subset of B, because B has an extra element that A does not. Okay? So I hope that that's kind of clear for you. All right, so with that, we're going to stop our conversation on set theory here. Monday's video we'll have the second portion to section 2.1. This is 2.1 part A. On Monday, you're going to have section 2.1 part B, along with the homework assignment. There will be a homework assignment that goes with this section as well. 2.1 has a homework assignment. It's already listed on your tasks, under your tasks tab in Blackboard. But just in case, I will state it here. Your homework, this is homework number 2 now, which is officially assigned as of tomorrow by our live Zoom class, which is 1 p.m. So by 1 p.m., this homework assignment is now assigned, and it will be due by 1 p.m. on Monday. So you, in essence, have all weekend to work on it. And homework number 2 is pages 51 to 52 in the textbook. Once again, for those of you who might have missed it, this is our textbook. Okay, it's mathematics for elementary school teachers, contemporary approach. This is the 10th edition. It's okay if you have a newer edition. The book itself has not changed much, and the only thing that might have changed is the order of things are a little bit different, but you'll have to let me know if your numbers or your questions don't match up to the ones I'm mentioning here. We have yet to run into that issue though so far, so fingers crossed. Again, this is homework number 2. It is being assigned officially as of 1 p.m. Friday, and it will be due by Monday at 1 p.m. And it is page 51 to 52, and you need to do numbers 1 through 9. Okay? All right, guys, good luck. I will see you tomorrow at 1 p.m. for our live session. I want to use that time to help some of you get give you an opportunity to ask me questions, rather. Apologies. But also to help you troubleshoot a couple of the things. I've gotten several emails about how to submit documents and where to find information. So I want to make sure that we can go over that in person and that we can make sure that everybody's on the same page and we don't have any issues moving forward. All right. Have a wonderful evening. And I'm going to go ahead and stop my share here. Take care, guys.